We've got questions on a couple of problems, and let's take this one. We want to add 1 over x minus 2. 1 over x minus 5. Now, to do this, we want to have a common denominator. The common denominator in this case is going to be x minus 2 times x minus 5. Neither one of these denominators factors in any way, and they're different, so they're relatively prime. Okay, they have no common factor, so the common denominators got to be the product of the two denominators. Common denominator is the smallest. It doesn't have to be the smallest. The least common denominator is the smallest denominator that contains all the factors of each of the denominators. Okay, now in this case it's fairly simple. This denominator contains x minus 2 as a factor, and this one contains x minus 5 as a factor. The reason we need a common denominator is because we can't add fractions with different denominators. Okay, so we get 1 over x minus 2. Okay, I generally make one mistake every day, so I got it out of my system. And I obviously won't make any more. Mistake is simply I wrote down the 2, or I wrote down the minus and didn't leave myself room for the minus. Okay, there we go. Okay, if we take this and multiply it by something that gives us an x minus 5 in the denominator, then we'll have that common denominator. Okay, well, if I multiply this fraction by anything except 1, it's going to change its value. We can't change its value, so what we do is we multiply by x minus 5 over x minus 5, which is just equal to 1 unless x happens to equal 5. Okay. And if x happens to equal 5, then this is 0 over 0, which is undefined. Indeterminate. Okay, so our point is we multiply by x minus 5 over x minus 5, because now when we multiply the fractions, our denominator will be x minus 2 times x minus 5. That's going to give us the common denominator. And then over here, I'll multiply by x minus 2 over x minus 2. So now we have the same denominator in both fractions. If we multiply everything out, see that we're going to get x minus 5 over x minus 2 times x minus 5 plus x minus 2 over x minus 5 times x minus 2, which of course is the same thing as x minus 2 times x minus 5. Okay. So now we have the same denominator. Algebraically, we could factor 1 over x minus 2 times x minus 5 out of this whole thing. And we'd end up with that reciprocal times x minus 5 plus x minus 2. Or we can just go by the rule, okay, which is if we have the same denominator, we can add these things. We can formally prove that just by factoring out reciprocal x minus 2, x minus 5. But we're not going to get that form. And we'll go by the rule. Same denominator. Now we can add the numerators. And the numerators are going to sum up. I'm going to write it out real explicitly. And we add the numerators, and that's all over the common denominator. And then we're going to get, of course, 2x minus 7 over x minus 2 times x minus 5. Another final point, we don't want to multiply these two out. We don't want to expand this denominator until we've completed this form, because in this form, we can then see whether something in the denominator, so one factor of the denominator, one or more factors of the denominator, can divide into a numerator. Okay, but it's clear that the numerator and denominator don't have any common factors. And then we can, if we wish, expand this denominator. To get this form. As far as I'm concerned, this form is more or less optional. I'd like to see things in factor form, because that's the form in which we can actually do things with the expression. If it's in this form, it's a little bit more mysterious. But there are also the reasons sometimes we want to have this form. So be sure you can put it in either form. Okay, we have the equation 2x squared minus 8x plus 17 equals 0. And on the review sheet, it did say solve this quadratic equation. I identified it for you as a quadratic equation. Usually, or very often, if you're doing a problem, and you'll come up with an equation that isn't quite in this form, but it's quadratic. So you always have to be able to identify that you do have a quadratic equation. Once you do, then you have actually three options. You can solve it by completing the square. You can solve it using the quadratic formula. You can solve it maybe by factoring. We can check the discriminant. If that square root of b squared minus 4ac isn't something we can take the square root of and get a square root in rational form, then, excuse me, then we're pretty much stuck with either completing the square or the quadratic formula. Okay, well, the quadratic formula. Okay, well, first of all, I'll just write out. The discriminant is the square root of 8 squared minus 4 times 2 times 17. And that's the square root of what? Well, square root of 17, 8 times 17 is 126, if I've got my arithmetic right. And 126 is bigger than 8, so it's a negative. Okay, so the two things we can tell already, we're going to get a complex solution. The other thing is, if we subtract 126 from 64, we get, I'm thinking on the paper I saw it's 72, but I think we get 62. And I was going to do something with that 72, but I can't do it with the 62. Let me just check. Your work is really the only reason I wanted to address this problem was to do one more step in simplification at the end. Okay. Okay, my mental arithmetic, that's a little worse than it's accurately do 8 times 17. Seems like I added 56 and 60 instead of adding to 70 rather than adding it to 80. Okay, anyhow. It comes out 72. Okay, so now I can do what I intended to do. All right, so now square root of 72 is irrational. It's not an integer. And it's not a simple fraction. It's not a rational number. Okay, it's irrational. So we use a quadratic formula. Or completing the square. Now, both these are things that people should come in to pre-calculus course knowing perfectly well how to do, even if they don't quite remember it. Yeah. But that's not the way we're saying it in this part of the Commonwealth at this time. Okay. COVID being one problem and difficulties. Okay, so we use the quadratic formula to complete the square. The quadratic formula and I'm not going to write out the quadratic formula, I'm just going to substitute into it. It's negative b, which is going to be 8. B being negative 8, plus the square root of, well, I've already written it out once. It's this. That's going to be 8 plus and minus. I got 72 here. It's negative 72, right? Yeah. Okay, now we get 8 plus or minus square root of negative 72 over 4, which is then 8 over 4 plus or minus. Okay, the square root of negative 72, of course, negative 72 is negative 1 times 72. The square root of negative 1 is I. Square root of 72 is the square root of 72. Okay, so 8 over 4 is 2. Now, the square root of 72. Okay. What's the prime factorization of 72? When we divide 72 by 2, you get 36. Divide it by 2 again, you get 18. Divide it by 2 again, you get 9. Okay. And 2 times 2 times 2 is 8. So it's the square root of 8 times the square root of 9. Of course, square root of 9 is square root of 3 times square root of 3, right? But it's then I'll write it out this way. 5 times the square root of 2 cubed times 3 squared. Useful when you, well, it's a little bit of overkill in this case. To do the whole prime factorization, but it often isn't. So it's always a good idea to do your prime factorization. Unless things are just perfectly clear. Okay, well, I can write this as 2 plus or minus I times okay, I can write 2 squared times 3 squared. Actually, this is unusual. I made a second mistake. Okay, it's going to be on that. Anyhow, I can do square root of 2 squared Square root of 3 squared, square root of 3. There's shorter ways to write it, but I'm going to do it this way. So that's 2 plus or minus I times 2 times 3. And the square root of 3, and that's divided by 4. Well, 4 is 2 times 2. 2 will divide one of those 2s, and you're going to end up without the 2 here. You're going to have a 2 in the denominator. And you'll still have the 3 times the square root of 3. And often then we'll write that as, I'm in the habit of writing the real coefficient first and then the I second. Other people have the convention of writing the I first. It's easier to see if it's on the end. I spent 2 years of graduate school studying functions of complex variables and beyond. So that's a little bit of a habit. It's not really that hard to break. I'll just mention it. I've got ingrained preference to see it this way. Although if you really want to see it the other way, I can write it that way. It's valid either way. Okay, so that's a lot more detail than is probably is necessary for this problem. When you look at that square root of 72, among other things, you can see that that's 8 times 9, right? Okay, and 8 has a perfect square in it, which is 4. Okay, so you can factor that 4 out. So you can write that as a square root of 4 times the square root of 2 times the square root of 9. Okay, the square root of 4 is just 2, so you would get 2. Square root of 9 is 3, so you get to 3. Okay, if the numbers are a little bigger than that, a little more stubborn, you have bigger prime factors. It's useful to do the prime factorization, because then if you do your steps correctly, it's always going to work out. And, you might not cancel anything, but at least you'll know if you have it in the most simplified form. Okay, you didn't have this mark. I just looked at what you did, and you did it exactly the way I'm going to do it. So one of us must be wrong. It's what you do is right. Okay, this equals means 1 divided by x plus 6. Anytime you have a fraction in the denominator, could be a fraction over a fraction. It could be even more complicated than that. But you always remember that whatever's under the fraction, something you're dividing by. So you can write that as a division. And then, of course, that is multiplication by reciprocal. That's what those things.